You click Download on a new AI model. Maybe it's labeled Qwen 8B or Llama 32B, and watch dozens of gigabytes stream onto your hard drive. That massive file contains no encyclopedias of human knowledge and no lines of logical programming code. If you open up that file, you will find a single static list of floating point numbers. The letter B tells you exactly how many of those numbers are in the file. In machine learning, we call each of these individual values a parameter. This raises a difficult question. How does a massive, unmoving list of decimals possess the ability to write Python code or reason through problems it has never seen before? Think of a parameter as a physical control knob that adjusts the flow of a signal. On its own, one knob does almost nothing. Most of these are weights, which act like resistors to decide how strongly one piece of data influences another. The rest are biases, which provide a baseline offset for the system's calculations. When an AI model is first created, all 8 billion parameters are set to small, random numbers. At this stage, any prompt you give it results in complete gibberish. Training begins by feeding the model an incomplete sentence and forcing it to use those random numbers to predict the next word. When it predicts table instead of mat, the system generates an error signal. Backpropagation traces that error backward through every connection, calculating how to nudge those 8 billion knobs to make the prediction more accurate next time. After trillions of corrections over massive datasets, these numbers settle into a highly tuned pattern that captures the structures of language. Once training is finished, the parameters are frozen. The intelligence of the model is a record of those trillions of past corrections. These frozen parameters occupy the transformer architecture. At the bottom, the embedding layer translates human text into mathematical vectors. Next, the attention mechanism maps out context, identifying relationships between words. Finally, the massive feed-forward network transforms these representations into answers. It is a structured assembly line designed to convert language into math, weigh the context, and compute a statistical prediction. A 70 billion parameter model can absorb more obscure patterns and complex linguistic structures than an 8 billion parameter model. However, every parameter occupies physical space on hardware memory. Each number must be stored and processed on chips like the GH100. While an 8 billion parameter model fits on a single high-end graphics card, a 70 billion parameter model requires these massive server arrays just to function. The mixture of experts architecture serves as a modern workaround for these hardware constraints. By activating only a fraction of its total parameters, for example 37 billion out of 600 billion per word generated, the model saves significant compute time. Scaling AI capability has become a direct confrontation with the physical limitations of hardware memory. Parameter count alone is a poor metric for quality. Training data and architectural efficiency often determine which model actually performs best in the real world. At its fundamental core, the text generation process consists of billions of carefully calibrated values executing rapid matrix multiplications. Running a language model means executing a machine's learned skill. Billions of numerical adjustments, frozen into a file, performing the math necessary to predict the next logical step in a sequence.